Hello, everyone. Welcome to the All Lab Script Trading Group, 19th of May, 2025. Few reminders. We have a Notion page, we have a mail list, and the links will be attached in the description to the YouTube video if you watch on YouTube, or they are attached to the emails that you got, invitations to this. The duration is 1 hour, and it's the questions during the talk are very welcome. So if you want to ask a question during the talk, please do. Clearly, obviously, when the speaker is giving you time to do so, or raise your hand. Please only use chat for necessary questions, and if you want to ask something, it's a bit better to ask it in person. But yeah, put the question in the chat if you don't want that. That's also fine. A very small advertisement. If you're interested, if you're a PhD student or you know a PhD student and you're interested in working on roughly decentralized storage solutions and zero knowledge, please let us know. We might be maybe looking into opening a position for summer internship. It's yet undecided, but yeah, if you're interested, just drop us a line. Okay, now getting to the speaker and the talk. Today, I'm very happy to welcome Hossein Hafezi, who is a PhD student at New York University working with Joseph Bonneau and Benedikt Bünz. Hossein's interests are in the design and application of proof systems. Hossein will be giving a talk on the recent work with George Kadianakis, Arantxa, Zapica, and Benedikt Bünz, presenting a multilinear commitment scheme. Presenting the sublinear accumulation scheme and the commitment scheme underneath. That's very exciting work, Hossein. Thank you for coming. And yeah, I'll now hand over to you.
Thank you for inviting me. Yeah, so I'll be presenting today KZH-Fold. The full name of the paper, I think, is like Accountable Voting from Sublinear Accumulation. This is joint work with George and Arantxa at Ethereum Foundation and me and Benedikt at NYU. So before starting the talk, let's see a bit of background. So I'm sure everyone knows this, but I still have to go through it. So what is incremental verifiable computation, or IVC? So IVC is a verifiable computation for a class of computation like the one you see on the diagram. So in which you're iteratively computing a function f such that input to each state is the output of the previous step. And PCD is a relevant concept which generalizes IVC from straight lines to directed acyclic graphs. So what I mean by that, if you look at the model of IVC, it's like a sequential line, but so it doesn't really allow you to do distributed proving or parallelism. But you can generalize it to PCD. For example, instead of having a straight line, you can have a tree, and it allows you to do parallelism and distributed proving. Next, I want to talk about non-uniform IVC, or PCD. So if we take a look at the model of IVC, we have a single function f, and we're iteratively computing function f. But what happens if instead of a single step function f, you can have multiple predefined instruction fi's, and each step you can select one of them and run one of them? And this is essentially what happens with non-uniform IVC, or PCD. And the motivation for it is essentially a verifiable ZKVMs, or like a verifiable CPU, where each of those FIs would correspond to one of the instructions in your CPU. Okay, now let's see how was IVC traditionally constructed. So traditionally, IVC was constructed via this augmented circuit, which had the following subcircuits. So this augmented circuit consists of a subcircuit f, which is the actual function you want to compute, plus this function, this other function, which we call the recursive overhead, which was essentially a snark verifier subcircuit. And what this snark verifier subcircuit would do is essentially just take a proof of correctness for the previous step and verify it, and that's it. But what was wrong with this model? So what was the motivation that this model essentially changed? Basically, snark verifiers are concretely very expensive to be implemented in the circuit. And why is that? Basically, all the snarks we know, the verifier is either non-constant, the size is not constant, or it includes, for example, pairing operations, which are very expensive to be implemented in the circuit. And this led to this paper Halo. And basically, the observation by Halo was we don't really need to check all these proofs of intermediate steps like at the same step. But what if we have like this mechanism that we can defer checking all these proofs to the last step and just check it at the last step? And this is essentially the motivation for accumulation schemes. So what are accumulation schemes? In very high level, assume you have two NP languages, LPy and LACC. So what an accumulation scheme does is that it reduces satisfiability of instance of LACC and LPy to a single instance in LACC, while satisfying completeness and knowledge soundness. And what I mean by that is like, so completeness means like, if ACC prime is satisfied, then we want, basically ACC prime is satisfied if and only if ACC and pi are satisfied. And by the way, the satisfiability function of LACC, we just call it decider. So whenever I say decider, I basically mean the satisfiability function of LACC. So completeness essentially means like ACC pi is satisfied if and only if the ACC and pi were satisfied. And knowledge soundness means that like if you have a witness for ACC prime, then essentially you're going to have an extractor and it's going to let you extract a witness for ACC and pi. And this is pretty much the standard definition for accumulation. But another property we wanted to add to the definition of accumulation was like sublinearity. And what I mean by sublinearity is that we basically want the size of the instances in LACC to be smaller than the original statement pi. So basically, we want this. We want any instance in LACC to have a sublinear size in terms of like the size of pi, where pi is an instance in LPy. And we also want the satisfiability function of LACC to take less time than the satisfiability function of LPy. So it means we want the decider to be sublinear in verification time of pi. And just to give you some intuition, by the way, every snark essentially gives us a trivial accumulation scheme. And since snarks are like sync-synced, every snark essentially gives us a sublinear accumulation, but we just call it like a trivial sublinear accumulation. And this is not like our primary interest. Anyway, so I told you like how like IBC was traditionally built. And I told you about the observation by Halo, where like, the observation where like instead of verifying all the proofs at the same step, we can somehow like defer them to the last step via accumulation schemes. So now let's see concretely how we can build IVC from accumulation schemes. So the high-level idea is like to simply replace the snark verifier with the accumulator verifier. So what happens at each step is that instead of verifying the proof, you simply accumulate it with a running accumulator and send it to the next step. And essentially, after n step, in the last step, you get a single accumulator. And by checking its satisfiability, it means that all the proofs from the intermediate steps were satisfied. And this is pretty much like the high intuition of how you can build IVC via accumulation schemes. And this is formalized with the BCLMS compiler. So what BCLMS compiler says is essentially, if you have a NARC, and for the NARC verifier, you have an accumulation scheme, then essentially you can build IVC from it with the following properties. So the IVC proof is going to be equal to your accumulator size. The IVC verifier is going to be equal to the decider time of your accumulator. And the IVC prover time is going to be equal to the prover time of your NARC plus the prover time of your accumulator. And by the way, when I say the prover time for your NARC, I mean for the augmented circuit. So this is pretty much where the recursive overhead reflects in prover time. And so the observation is like, if we have a sublinear accumulator, according to the BCLMS compiler, we can essentially compile it to an IVC or PCD with sublinear proofs and decider. That's because like the IVC proof is going to be equal to the accumulator, and we know it's going to be sublinear according to the definition of sublinear accumulator. And also the IVC verifier is going to be equal to the decider time, and again we also know that's going to be sublinear. So yeah, essentially that's like our primary motivation: build a sublinear accumulator, so the resulting IVC or PCD would have sublinear proofs and decider. However, before going through our constructions, I very quickly want to go through Nova. So there is this term trivial narc. I'm just going to use it. I thought this might not be the worst idea to include a slide for it. So assume we have a prover which has an instance X and a witness W, and a verifier that has only has the instance X. So when I say trivial narc, I simply mean when the prover simply sends the witness to the verifier, and verifier would basically run the NP verification by itself to see if W is a satisfying witness. All right, back to Nova. So what Nova does is that Nova builds an accumulation scheme for the trivial R1CS narc with the following properties. And by the way, when I say N here, I basically mean the instance plus witness size of the R1CS. So Nova accumulator has the following properties. The accumulator size is going to be linear in terms of like the original R1CS circuit. The prover time and the decider are also going to be linear. They're essentially going to be an MSM on the size of the instance plus witness of the R1CS. And finally, the verifier circuit is going to be constant, and concretely, it's going to be very efficient. So it's going to be 2 or 3 scalar multiplications. And this is primarily the reason that like Nova is like very interesting for people in practice, because the verifier circuit is like super small. Now, given this accumulator scheme for the relaxed R1CS, with the BCLMS compiler, they can compile it into an IVC scheme. So the IVC scheme by Nova will have the following properties. So the IVC proof size is going to be linear because the accumulator size was linear, and the prover time and the decider time are also going to be linear because essentially the accumulator, prover, and decider time were linear. Now to give you some intuition of like how this linearity really comes into play into practice and why it's going to cause trouble, let's basically see an example. So consider a function f to be 1 million R1CS constraints. What happens is that the accumulator size for this function is going to be around 80 megabytes, and the decider time when you run it on my laptop is going to be around 4 seconds. And basically 1 million constraints is not a lot. So this is going to cause us trouble, especially with distributed proving, as I will demonstrate in a couple of slides. But what is Nova and recently Micronova's solution for it? So their solution is just like, in very high level, run a ZK snark at the last step of IVC to reduce the prover size. And it actually works, but it does come with a few downsides. So first of all, this ZK snark prover's time is going to be 24x compared to the prover time for one single step of IVC. And also the proofs, this ZK snark proof is not going to be incremental. And what I mean by that is like, so if you need simply proof of correctness for the intermediate steps of IVC, it means you have to run the ZK snark multiple times. And that means like more prover time. I will essentially demonstrate it in a couple of slides when I demonstrate the motivations. Any questions so far?
I did want to ask like a very, very small question. So like 3 slides ago, you mentioned that the recursive overhead, so-called recursive overhead, the subcircuit was very fast. Just to remind people, that is, as far as I remember, that is because you just combine the commitments to the witnesses, right? The KZH commitments. That was the original idea of the compiler, or?
Yeah, basically you just do 2 or 3 scalar multiplications, which is like the homomorphic operation.
So the accumulator here is like accumulator size is the actual plain text witness, and the verifier circuit combines commitments.
Yeah, exactly.
Okay, perfect. And then, sorry, just for the compiler, the why was the proof size linear here?
Because essentially that's like what the BCLMS compiler does. So the proof size is essentially going to be to your accumulator size.
Okay, so this implies attaching the witness to as a proof.
Sorry, could you repeat that again?
So the accumulator size is linear. The accumulator size is linear, and I was assuming that Nova itself already. So again, Nova IVC is without the last snark, so it's just the accumulation scheme in the middle.
Yeah,
which is why
exactly.
you say the proof size actually includes the witness in plain text, which is why it's linear.
Yeah.
Okay, perfect. Thank you.
And this is also the case for almost, not all of them, but like almost all previous accumulation schemes, except for one exception. For example, hypernova, protostar, they all have like linear sized accumulators. Okay, let's see motivations for this paper. Our first motivation, which is a very important one, is distributed proving. And I think this is an application which has been underlooked in many of the IVC papers. So assume we're doing distributed proving in a PCD setting, where like, so what happens is like me as the first prover, when I want to hand over the computation to the second prover, I have to send the second prover an accumulator. And the second prover, while receiving the accumulator, has to run the decider on it just to make sure the accumulator is well formatted and I was not cheating. So this means like our communication is essentially going to be dominated by the accumulator size. And second prover, before starting any meaningful computation, has basically has to run the decider, making sure I was not cheating. And so if the accumulator size is huge or the decider time is huge, it's essentially going to be a bottleneck. Now, it does get a lot worse when we are trying to do distributed proving of ZKVMs with IVC or PCD. And so what happens with the state of the art, which is supernova? Instead of sending one accumulator, you have to send a single accumulator per instruction. So it means if you're trying to verifiably run a CPU with 64 instructions, you have to send 64 accumulators to the second prover. And now second prover, instead of running one single decider, has to run 64 deciders. So it means like the communication and the waste time by the second prover just to run the decider, both are gonna scale linearly with the number of instructions. The other motivation we have is, so the motivation for a sublinear decider. So take a look at the diagram you see. It's basically the classic model of IVC, where like you're trying to iteratively compute a function f, you compute it for n step, and at the last step you simply run the decider. It means that you're only interested in the correctness of the last step and you have no interest in the intermediate steps. For this specific case, it might be fun if you have like a linear size decider, because you're essentially just going to run it once. But what happens is that like when you actually care about all the proofs of intermediate steps, and it means that like these proofs of intermediate steps are going to be the decider time is going to be linear. So if you want to do the solution by nova or micronova, it means you have to run the zk snark for all of these intermediate steps. But that essentially means it's just going to blow up your prover time by around like, I don't know, 24x. So the alternative that we're considering is that like, what if your decider is already sublinear, so it's already efficient? And so if I want to give you examples of like what are the actual applications where you actually care about the intermediate steps of IBC, this would include like clients, verifiable key directories, and Sing blockchains like Mina. Next, the other motivation, and it was pretty much the initial motivation for this paper, was distributed signature aggregation. And this is the part of the paper I'm least familiar with. So in very high level, what happens with Ethereum is that like Ethereum finality time is around 15 minutes. And this is mostly dominated by the signature aggregation computation. And if I want to just give you in high level how the signature aggregation looks, so assume you have this some sort of tree where like the leaves would be your validators and the internal nodes would be the aggregators, and they're like aggregating the signatures of the previous layer and would simply forward it to the next layer. So you have like these multi-layers, and at the end you basically get one signature for your proposed block. So the observation we have here is that like the computation of aggregators is essentially a BLS aggregation scheme, which is you're just trying to aggregate the BLS signatures. Plus, you're also trying to take union of some bit vectors. And what are these bit vectors? So essentially in their signature aggregation scheme, with each signature comes a bit vector, and this bit vector essentially says like who has signed and who has not signed the block for accountability reasons. So yeah, aggregators also need to take a union of two bit vectors to make like the new bit vector. So the observation we have is like this signature aggregation is a layered tree. So essentially you can model it with PCD. However, if you do it naively, it's going to be impractical because like this is like a P2P setting. It means like communication is going to be super important. And hence, you need, if you want to use PCD, you need a PCD where the proofs are sublinear. Otherwise, this is not going to be practical. And based on motivation, and with the proposed sublinear PCD scheme we construct a signature aggregation based on PCD with sublinear proofs, which has like the following properties. So essentially, we improve the verifier time and communication time of the current scheme by Ethereum by 5x, and based on that, we assume that we can improve the finality time of Ethereum by 5x as well. And yeah, we're essentially comparing to the system of Ethereum, which I believe is plain aggregation of BLS signatures. So it doesn't involve any proof systems or anything. Okay. Any questions so far for the motivations? Okay, cool. Now let's see our contributions. So as our first and most important contribution, we construct KZH. It's a polynomial commitment scheme with sublinear opening. And in fact, it has like some very cool properties as well. I'll point them out. And next, we design a sublinear accumulator for KZH. And essentially, based on that, we build an IVC or PCD with sublinear proofs and verifier. And based on the PCD scheme we have designed, we construct a signature aggregation scheme for Ethereum. And finally, and orthogonal to the other contributions, we introduce a new approach to non-uniform IVC and non-uniform PCD. And our non-uniform PCD is essentially the first efficient non-uniform PCD, and it has nothing to do with KZH. It can be initiated with any polynomial accumulation scheme, and it doesn't even require homomorphism. So yeah, and what I mean by efficient non-uniform PCD is that like our non-uniform PCD, the prover time does not depend on the sum of all the instructions, and this is unlike all the previous work, which includes supernova, protostar, and kilonova. I'll elaborate on that hopefully. Now, also, if you want to see some numbers, so we have basically implemented our IVC scheme, which we call Spartan plus KZH-Fold, and we have also implemented Nova, and we have done a quick comparison. So for a circuit which has like 2,000 Poseidon hashes, which is almost like a million constraint, our prover time is almost 3x worse than Nova, which was pretty much expected. So we were expecting something like 2x. However, our implementation is not super optimized. But our verifier time is like 50x better than Nova, because ours is almost like square root, while for Nova is linear. And our accumulator size is like 2000x better than Nova. For Nova, it's like 80 megabytes, but for us, it's just like 40 kilobytes. Okay. Now I wanna describe how we can like construct KZH and what is the starting point for it. So we saw like our goal so far is like to build an IVC scheme with sublinear proof and deciders. And according to the BCLMS compiler, it means we need to build a sublinear accumulation scheme. And the very key observation we have here is that like if we can build a polynomial commitment scheme with sublinear predicate or a sublinear opening, then essentially it's going to result in a sublinear accumulation scheme. So our goal will be essentially the following. So we want to design a PCS with the following properties. First, we want it to be homomorphic. And the reason we want it to be homomorphic is basically we want it to be compatible with protostar, which is the recipe, which is the technique that is going to help us to build accumulation scheme. Next, we want the commitment to have like a constant size. And again, the reason for that is because like the commitment size is essentially going to be reflected in the circuit size. So for example, if your commitment size is 5, it essentially means for a homomorphic operation, you need to do 5 group scalar multiplications, which in the circuit language, it means like you have to do 5 scalar multiplications in the circuit. So ideally, we want the commitment size to be constant, and very ideally, we want it to be just a single group element. Next, we want the opening size to be sublinear, because I mentioned it's going to result in a sublinear accumulation scheme. And next, we want the verifier checks to be algebraic and low degree. And again, these are because like we want to be compatible with protostar. Essentially, if you have like low degree verifier checks, the accumulation scheme is going to be more efficient. And finally, we don't want any degree 2 pairings. So we just want degree 1 pairings. And what I mean by degree 1 pairings is that these pairing checks where like one side is prover so one side of the pairing is prover defined and the other side is just constant points from your SRS. And the reason, so this is like very crucial. And the reason we care about it is because if you have degree 2 pairings in your verifier check and you try to build an accumulation scheme for it, it essentially results in some error terms which are going to be target group elements. And target group elements in practice implemented in the circuit are going to be like very inefficient. So that is one thing we're trying to avoid. Okay, now let's see concretely how we can build KZH and its accumulation scheme KZH-Fold. Our starting point to build KZH is Hyrax. So just to give you a reminder, Hyrax is this polynomial commitment scheme with square root opening size. And according to what I said, so if you have a polynomial commitment scheme with sublinear opening size, you can build a sublinear accumulation scheme from it. And if you want to build an accumulation scheme for Hyrax, essentially you can do it. And you can build an accumulation scheme with a square root accumulator size, which is great, which is pretty much what we wanted. However, the problem with Hyrax is like the commitment size is square root group elements. And it means that in the circuit, when you're trying to take a linear combination between 2 commitments, you have to do square root scalar multiplications, which is going to result in high recursive overhead. So, yeah, that is pretty much like we're trying like to modify Hyrax in a way that we make the commitment size constant in a way. And again, just to give you a reminder, the way Hyrax works is that you put your polynomial coefficients or polynomial evaluation points in a matrix. And so what you do is like you have these set of generators and you commit to each row separately. So you're going to have like these commitment CIs, which are essentially going to be commitment to each rows. So that is why the commitment size is square root. And that is also why like the homomorphism operation is going to be like a square root group operations as well. Okay, now our idea to build KZH is just like a very small modification to Hyrax. So what we do is like we change the untrusted setup of Hyrax with an SRS, and it helps us essentially to get a constant commitment size. And essentially our commitment size is just going to be 1 G1 element. So what happens is that assume we have this SRS and you commit to the whole matrix with this SRS and you get a single commitment C. However, similar to Hyrax, we're also going to still commit to these rows and we're going to just call them DIs. So these DIs are essentially going to be commitment to your rows. And the key thing that will sort of connect KZH and hierarchy is that you prove via pairing that commitment C and commitment DIs correspond to the same matrix. And once you prove that, you can essentially use the opening of hierarchy and the DIs to open the polynomial. So yeah, the hierarchy, the KZH opening will essentially include the commitment DIs plus the hierarchy opening. And the KZH verification is essentially checking that C and DIs are consistent via the pairing check I just mentioned, and then running the hierarchy verification, giving the hierarchy opening and the DIs. And one very cool thing about KZH is that like these commitment DIs are already pre-computed. So you don't have like to compute to them again online when you're trying to opening it. You can just do it at the commitment phase and that's it. If you want to check out the properties of KZH, so assume you have a multilinear polynomial f on a Boolean hypercube of size L. So its properties are going to be as follows. So the commitment size is essentially going to be linear group operations. Essentially, it's just going to be an MSM. The proof size is going to be square root, and the opening time is going to be linear, but it's going to be field operations, not group operations. And in practice, field operations are like much cheaper than group operation. And the thing is that like this opening size is not something you can actually avoid, because the main cost of the opening is dominated by the polynomial evaluation. So essentially you have to do it. And finally, the verifier time will be dominated by a multi-pairing of size square root. Next, so what we do is like, so basically we build KZH inspired by hierarchy. And the idea of hierarchy was like to put the matrix coefficients in a matrix, the polynomial coefficients in a matrix, and try to commit to the matrix in an intelligent way. However, we see that we can actually extend that idea. Simply, you can think of a matrix as a tensor of degree 2. So a cube would be a tensor of degree 3, and so on. And essentially, with this idea of like putting the matrix coefficients in a tensor, we construct KZH-K. So the basic idea is like we put the matrix coefficients in a tensor of degree K, and we get like lower verifier costs at a cost of higher opening and higher commitment cost. So the cost of KZH-K are as follows. The commitments cost is going to be essentially K times N. So if your K is constant, it's essentially going to be just like linear time. The opening size, the opening cost, if you do some sort of pre-processing, it's again going to be square root. And the verifier cost is going to be K times N1 over K. And concretely, when you put your K equal to 4 or 5, this is going to be very close to logarithmic. So this is going to be like very useful when you really care about the verifier cost. Okay, so far we have designed the KZH polynomial commitment scheme. We know it has a sublinear opening. And now with Protostar, we try to build an accumulation scheme for KZH verifier. And according to Protostar and the fact that the opening size of KZH is sublinear, we know that our accumulation scheme is going to be sublinear as well. So the observation is that the verifier function for KZH essentially includes some degree 2 scalar multiplications plus a degree 1 pairing check. And with the Protostar compiler, so Protostar compiler is like very generic. And based on that compiler, we build KZH-Fold, which is going to be our accumulation scheme for KZH. And it's going to have the following properties. So the accumulator size is essentially going to be almost equal to the opening size of KZH, and it's going to be square root. The decider time is going to be almost, again, equal to the verifier time of KZH, and it's going to be square root again. However, the prover time is going to be linear, and that's because like you essentially have to commit to the witness once. And our verifier complexity is going to be 3 or 4 scalar multiplications plus a constant number of field operations, which is okay. It's equal to Protostar's number of scalar multiplications, and it's just like one extra scalar multiplication when you compare it to Nova. And we can also build like an accumulation scheme for KZH-K, and it's going to have the following properties. So the accumulator size and the decided time from square root is going to be down to k times n1 over k. However, the recursive overhead will be k plus 1 or k plus 2 scalar multiplications instead of 3 or 4. And concretely, when you put some k equal to something like 4, yeah, it might be essentially worth it for some applications, since the decided time and the accumulator size like will be like really low. If I want to give you like a quick comparison of KZH-Fold with other schemes, so if you just want to like compare it to Nova, so Nova's recursive overhead for IBC is like 2 group operations. However, for KZH-Fold, it's going to be like 3 group operations. But the decider time of Nova is going to be an MSM of size n, but for us, it's going to be, for at least the KZH2, it's going to be like a square root pairing operations. And finally, our accumulator size is a square root, while for Nova, it was linear. I also want to give a quick comparison to Halo. So Halo is like sort of like a sublinear accumulation scheme in the sense that the accumulator size is logarithmic size. However, its decider is linear. But basically, the problem with Halo, and I think it's the reason it hasn't been really deployed in applications, is because like the recursive overhead is concretely high. So it's going to be logarithmic number of scalar multiplications compared to Nova or these recent accumulation schemes where they have like a constant recursive overhead. Any questions so far? So next I'm going to explain like how we can build IVC and PCD for R1CS from polynomial accumulation. Cool. If you're curious, what is this bird doing here? So basically, we came up with some name for the accumulation scheme, but then we changed it to KZH. But I still love the bird. I just wanted to keep it in the slides. So the idea that the way that we want to essentially build accumulation scheme for any NP language, given an accumulation scheme for a polynomial commitment scheme, is that like, so in very high level, we translate the NP language we have with the PIOP into some polynomial checks. And with the polynomial accumulation scheme, we're simply going to just like accumulate those polynomial checks. And concretely, what we do is like we take R1CS as our NP language, and we translate it via Spartan into some polynomial checks, and we just accumulate those polynomial checks with the polynomial accumulation scheme we have. And by the way, there is nothing special about R1CS or Spartan. We believe you can essentially use Plunkish and other NP languages as well. But for implementation reasons, we just decided to go with the Spartan because it already has a code base which is compatible with ArcWorks. Okay, so we have the R1CS and we translate it via Spartan into polynomial checks. And essentially what we get is like, we get a witness polynomial W, we get an evaluation of W, plus we get some evaluation points for sparse matrices A, B, C. And the way we're going to accumulate these is we're essentially going to have like 2 different strategies for them. So the witness polynomial, we're essentially just going to interpolate it as a PCS and accumulate it. However, we don't want to use the same technique for the sparse matrices ABC. And the reason is like, if we want to interpolate ABC as KZH, the SRS is going to be so huge. So instead we take like a different approach, a better approach, I think. So if we look at like this matrix evaluation relation, so what it really tells us is like the relation is like essentially what it is as it follows. So if you have matrix A, the sparse matrix A, and you consider its multilinear extension A tilde, So the relation is essentially as follows. You have two evaluation points, Rx and Ry, and you have the evaluation Z. And you essentially just want to say like the relation is just like when you evaluate A tilde at Rx and Ry is going to be equal to Z. And we see for this specific relation, we can build a very efficient accumulation scheme based on Polynomial, and it's going to have the following properties. So the prover cost is going to be just logarithmic evaluations of A tilde. It's going to be outside of circuit. We have implemented this, and in practice, it's going to be very efficient. The verifier cost, which is going to be the recursive overhead, is going to be logarithmic field operations. And the proof size is also going to be logarithmic field operations as well. And yeah, just note that this is like field operations, not group operations. It essentially means if like your circuit is like 1 million constraints, a logarithmic number of field operations is essentially going to be like, I don't know, 20 more R1CS constraints. So it's not a lot. Like the cost is like very negligible. Anyway, back to where we started. So we had the R1CS, we translated via Spartan into the witness polynomial and some sparse matrix evaluations of A, B, and C. So we decided to interpolate the witness polynomial as our PCS scheme, for example, KZH, and then accumulate the PCS, accumulate this with a PCS accumulator scheme, for example, KZH-Fold. And we also have these matrix evaluations, and we're gonna essentially accumulate them directly with the accumulation scheme we built from it. So our augmented circuit will be essentially as it follows. So we have the Spartan verifier, which is essentially going to output some witness evaluation and some matrix evaluations. We're going to handle the witness evaluation with the polynomial accumulator we have. For example, here it's going to be the KZH-Fold verifier. And we're going to handle the matrix evaluations with another subcircuit, which is essentially going to take some running matrix accumulators, and it's going to accumulate them with the new instances it gets and output the new running accumulators. So one thing I just quickly wanted to mention is that, like, if you consider our augmented circuit and you compare it to Nova, so basically you just realize it's like much more complicated, because like in Nova there is simply some function f and some accumulator verifier, but for ours we, instead of 1 box, we have like 3 boxes here. And the reason for that is because like we are translating the circuit into the polynomials, and then we accumulate the polynomials. But however, for Nova, it was different. So Nova was like directly accumulating the circuit. And that's essentially like why our augmented circuit is like more complicated. Any questions so far? Sorry, I need to get some water.
Simon, to check question. Sorry, I think like the last few slides. So regarding the last slides covering the accumulation. So you're actually, at which point the Spartan proof is being verified here? So the Spartan, can you describe what that is?
Oh yeah.
The sum check is outside of this box, right? So you don't do sum check here.
Yeah, so it's essentially gonna be like a partial Spartan PIOP, in the sense that like you know, when you partially verify Spartan, you get some zero check and you get like some sparse matrix evaluations. So what happens with the Spartan is like the zero check is executed. So the zero check is like very straightforward. It's just going to be some sum check and some evaluation of the witness polynomial at a random point. However, for the sparse matrices, if you try like to, so Spartan handles it with a Spark. But if you want to build an accumulation scheme for Spark, it's essentially going to be like more expensive, because it includes like memory operations and everything. But our observation is that like these 3 matrices, A, B, C, these are just going to be constant matrices. They're essentially going to be like part of the index for your relation. So we observe that we can build an accumulation scheme which is far more efficient than building an accumulation scheme for Spark. And basically, we already actually do know how to build an accumulation for Spark, and because of the memory operation it involves, we decided not to go for it because it was gonna have a much higher recursive overhead.
Okay, this makes sense. So this is not like a full verifier. This does some part of the sum check, but not all the whole sum check.
Yeah. So that's essentially just gonna be the sum check, exactly.
Okay. Okay, makes sense.
All right. Now, this is the second part of the paper, and this is the part that we just updated yesterday, actually. So we want to explain how we can build non-uniform PCD from any PCS accumulation scheme, and why ours will be far more efficient than the previous schemes. So if I just want to give you a quick comparison of the costs of our approach to the previous approaches, the previous approaches consist of supernova, protostar, and kilonova. And for all of these approaches, the prover time is going to be linear number of group operations in terms of the combined size of all the instructions. The verifier time is also going to be equal, so you're going to do a linear number of group operations in the combined size of all the instructions. And finally, the witness size is also going to be linear in terms of all the instructions you have. However, for us, the prover time is essentially going to be dominated by the maximum size of all the instructions, and our verifier time will essentially have two terms. So one term is going to be almost like group operations in terms of the maximum size of all the instructions, plus a linear term. So it's going to be a linear number of field operations in terms of the combined size of all the instructions. However, concretely, we know field operations are much cheaper than group operations. So our verifier time, concretely speaking, is going to be far way more efficient than previous approaches, because our linear term is field operations, not group operations. And finally, our witness size is also going to be dominated by the maximum size of all the instructions. And this is going to be generic for over polynomial accumulation scheme, and it does not even require homomorphism. So you can essentially, initiate it with base fold and these other hash-based polynomial accumulation schemes that exist. But yeah, so you can also initiate it with KZH-Fold, and since KZH-Fold has sublinear verifier time and sublinear witness size, your verifier time and your witness size are going to even look better. So, for example, concretely, if you initiate it with KZH-Fold, the prover time is essentially going to be dominated by the maximum size of all the instructions. The verifier time is going to have some square root term and a linear number of field operations, and the witness size is essentially going to be dominated by the square root of the maximum size of all the instructions. So this looks very good, but what is the underlying idea for it? The high-level idea, the high-level observation is that polynomials give us much more flexibility than circuits, in the sense that if you have two circuits with two different structures, we cannot accumulate them. But if you have two different polynomials with two different degrees, you can just assume they're a polynomial of the same degree, such that one with a lower degree has zero coefficients. So it means even when we have polynomials of different degrees, we can basically accumulate them very efficiently. And this is in comparison, for example, to supernova, where you cannot accumulate circuits directly. So for each different circuit, you need one different accumulator. But for us, it's not going to be the case. We can assume all these polynomials are the same, and we can just keep one running accumulator for them. One very interesting intuition for me myself was this is kind of the transition from Gross 16 to Planck. So Gross 16 was it was trying to directly prove a circuit, which is pretty much like what Nova is doing. So for Nova, it's also like you're trying to directly accumulate the circuit. However, for Planck, it was different. So for Planck, you have like this whole, method of like having a PIOP, translating your circuit with a PIOP into some polynomial checks, and then, handle the polynomial checks with a polynomial commitment scheme. And for us, it's going to be like very similar. So instead of like trying to accumulate those circuits directly, we translate the circuit into polynomials and then handle the polynomials with like polynomial accumulation scheme. And that's why it essentially gives us like more flexibility, which is pretty much the same reason that Planck has like a universal setup and it's like much more flexible than Gross 16. So concretely, what happens is like in a very high level, when we have like these instructions FIs, we can just translate them with a Spartan into like witness polynomials and some matrix evaluations of ABC. But here we're going to have like different ABC matrices for different instructions. And again, with the same strategy. So what we do is like we try to accumulate these witness polynomials with a running polynomial accumulator. So concretely, assume you have a running polynomial accumulator of degree capital D, such that its degree is going to be higher than the degree of all the witnesses we have. And we accumulate this witness polynomial with this running PCS accumulator at each step. However, for the matrix evaluations, AI, BI, and CI, we're gonna essentially take a similar strategy to Supernova. So what we do is like for each of these matrices, we're gonna have a running accumulator, and similar to what Supernova does, we're just gonna, with the memory arguments, we're gonna like select the right accumulator, the right running accumulator, and accumulate it with the current matrix evaluations we have, and output the new accumulator. So you may ask like, okay, your strategy also involves Supernova, so why is your scheme is like more efficient than Supernova? And the answer to that is like, so what the part of the witness that we are accumulating Supernova style is like logarithmically scales logarithmically with the original size of the circuit. And that's why if you look at like the cost of our scheme, we're going to have some logarithmic terms. But however, concretely, those are going to be very small. And that's why both asymptotically and concretely, we're going to be like much more efficient than Supernova. And thank you. Any questions?
Thank you all for saying we're actually very much on time. Yes, Mark, you had a question. Yeah.
Yes, hello. First, thank you for the talk. It was very interesting.
Thank you for listening.
I'm trying to understand if you can come back to the slide in which you present your transformation from polynomial commitment scheme accumulation to PCD. The one with yes, this one, perfect. Yes, yeah. I'm trying to. It kind of looks like I'm trying to understand how close that is from the Halo paper, in which you do get like, well, so they don't use R1CS, they use a Planckish arithmetization, but whatever, it's the same. And then they do accumulate everything that is related to polynomial check into one PCS accumulator. And then they run the other part of the verifier, which in your case is some check from this Spartan and some matrix evaluation, and in their case is some other things related to Planck. Like, it seems that it's very similar to me. It seems that if you, another way to say that is that it seems that if you instantiate the Halo 2 paper with your KZH, commitment scheme instead of the inner product argument they use, you would get something pretty similar. Do you think that is true or not?
No, that is definitely true. So I mentioned that like there is nothing special about R1CS. You can definitely use, instead of R1CS, for example, Planckish. And yeah, we actually so basically like what changes from this augmented circuit when you change it to Planckish So here you're going to have some sort of verifier for the Planck-ish, and you're going to have still like the verifier for KZH-Fold, but you're not going to have the matrix evaluations. And that's, I think, the biggest thing that changes when you change it from Spartan to Planck-ish. And as a matter of fact, we're actually working on a follow-up, so it's going to be with Planck-ish this time.
Okay, thank you.
So just to follow up on the question, I guess, can you return to the previous slide? Yeah, I guess the main difference is that, well, in terms of practical performance, would be that the accumulators here are actually square root of, I mean, if you use KZH-K or something, they will be even smaller, right? So the size of the accumulator here is kind of important. So it's the trade-off, I feel like, yeah, it probably looks more like Halo to me now that you said it. But the important part is, but the important part is the sizes and times of the decider, right? So the size of the accumulator is smaller, and then the time of the decider is also.
Yeah, honestly, like, this paradigm is like very generic, where you have a PIOP and you accumulate the polynomial checks. So it's going to be like very generic, and with different accumulation schemes, you're going to get like, I don't know, different accumulator sizes, different decider times, blah, blah. And Halo follows like the same paradigm.
Okay, this makes sense. I think we can take more questions if people have more questions.
I do have like one more slide, then thank you. So we're going to have like this paper out in a couple of weeks. It's called Benedikt, Transparent Dictionaries from Polynomial Commitment Schemes. And so I don't know if you are like familiar with transparent dictionaries. It's like, so transparent dictionaries are like the primitive underlying certificate transparency used by Cloudflare, Google, or the verifiable key directories, which are used by WhatsApp, Signal, and blah, blah. So we kind of like have this new paradigm of making transparent dictionaries from polynomial commitment schemes, unlike the previous approaches, which are like almost all of them based on trees. And the very cool thing is like, so we initiate this scheme with KZH. And the reason it's like so efficient is because, so KZH is like, has like some very cool properties. One of them is that when you want to open KZH at Boolean points, it's essentially for free. So it has almost like zero cost. And that's why we can essentially build this primitive very efficiently. So yeah, I just also wanted to mention that as well, because it's based on KZH as well.
That's perfect, yeah. So sounds great. It's quite interesting. So will you print it soon, or?
Yes, hopefully in like 2 weeks or 3 weeks, it'll be on ePrint.
Nice. I do have a question from my own. I feel like people don't want to ask questions. So can you please get back to like one of the earlier slides comparing Nova accumulation to the one that you built? I think it's like around 30, but maybe it's much earlier. Maybe this one, yes. There were concrete numbers. No, with the concrete numbers that you evaluated. So there was, something. Here we go. I think this one. Yes, yeah, this one. So I think I don't quite understand the numbers here regarding. So by after listening to the talk, and you have a similar table in the paper, I realized that the verifier here. So verifier here refers to not the Planck verifier. It refers to the actual IVC verifier, which is kind of like a decider for the decider for Nova, right? So why the verifier for your scheme is so fast and for Nova is so slow? I would expect yours to be slower because your deciders pairings, like a lot of pairings, and Nova's decider, if you actually put like a quant on top, that's actually kind of fast because it's just one MSM.
No, that's not actually true. So a linear sized MSM is like takes much longer than a square root multi-pairing. That's
okay. So the difference here is that you made the circuit extremely big, so it's like a 1 million, right? Constraints.
Yeah.
And so you do like one huge 5 second. Okay, is this like a single core thing or is it parallelized?
I think it was like single threaded, I think.
Okay, and you do a lot of pairings. You do like a square root of pairings. Is that correct?
It's like a multi-pairing. So I'm not sure like how ArcWorks implements multi-pairing or MSMs, but like they probably do it like both very efficiently. So they were like probably optimized by ArcWorks itself.
I would also say that if you're using ArcWorks directly, then it's probably also parallelized. But yeah, sorry, Mark.
Yeah, actually, about just a remark about the multi-pairing. What you only pay once the final exponentiation. So you do the Miller loop square root of time, but you pay only one final exponentiation, which is quite faster than square root pairing.
Okay, so would you? I guess my question is it fair to say quite a few times in the presentation, the paper, you mentioned asymptotic time of the verifier that is like k n to the 1 over k for the tensor variant of the polynomial commitment scheme, right?
Yeah.
But this isn't pairing, so I think given that the pairings are so much more heavy than the Can you comment on like how would it really compare in practice? So maybe Mark, you can also comment if you know the concrete numbers because I just don't remember them. Is it actually linear? Is it like does it become linear if you batch them?
I honestly don't know, but like we implement like these numbers you see here are like based on like the so these are like actually implemented protocols. These are not like mini benchmarks where we're trying to compare multi-pairing to MSM. So this is like we have actually implemented the IVC scheme for Nova and Spartan KZH-Fold, and these are like the concrete numbers I got on my laptop.
Sure. So 135 is the concrete number for like 1,000, like 1.5K multi-pairings.
Yes.
Okay, and also a small follow-up. So you mentioned something that if the second argument of the pairing is fixed, then you can implement the pairing within the circuit quite a bit faster. Is that what you're trying to say?
No. So basically, the way you try to accumulate these pairings is like, so when one side of the pairing is fixed and the other side isn't fixed, so you simply take a linear combination of the non-fixed sides, and it's going to be like group of scalar multiplications, and you don't have to do pairing in the circuit.
Right. Okay. So what you try to say is that there are no pairings in this recursive overhead subcircuit.
Yes.
Okay. Sure. Okay, this makes sense. I think yeah, thank you a lot. I think that's my questions.
And we were like very unlucky when we were like trying to implement this. So basically we have to pad our circuit to be a power of 2. And so you see like the circuit size was almost like 1 million, but since we had to pad it, even though it was with zeros, but it's still like the size essentially for us doubled up compared to Nova. I don't really know like how much this would reflect in practice.
I see. Okay. If anyone else has questions, then it's a good time to ask. Otherwise, 3, 2, 1. Let's wrap up. Again, thanks, Hossein, a lot for coming. Great presentation.
Thank you for having me.